Hi, welcome back to Accelerated Math 2. Today we're going to take a look at sequences, and specifically we're going to take a look at arithmetic sequences. Now, first of all, in general, a sequence is just a set of numbers that is characterized by some sort of definitive order. If we want to take a look specifically at some sequence, we'll take perhaps a look at the following. So 7, 11, 15, 19. What you can see here is that we've got a set of numbers that's just increasing by 4 each time. They have a common difference. And so if we were to make a prediction about the next term, 19 plus 4 is going to bring us to 23. This is what we call an arithmetic sequence. It increases or decreases by a constant difference every single time. And what we're really interested in today is how do we come up with a general rule that we can apply to any type of arithmetic sequence. And so an arithmetic sequence is characterized by 2 key parameters. As long as we know the first term is what we call A1, and the common difference, we can generate the entire sequence. To get from the first term to the second term, we simply add that common difference. So really, we know that A1 is really simply A1, but to get to the second term, we just take A1 and we add 1 difference. To get to the third term, well, if we start at the first term and we now add 2 differences, A3 will be equal to A1 plus 2 differences. And at this point, we can start to begin to spot patterns. The prediction about the fourth term, you might conjecture, would be A4 is really the first term, and we're now going to add 3 differences. If you wanted to get to the 50th term, you would start at A1 and add 49 differences. And in general, if you wanted to get to the nth term, that's the term in position n, you'd start at the first term and you'd add n minus 1 differences. And that's really how this explicit rule is determined. The explicit rule, all I need to know is I need to know the value of n, where n represents the position in the sequence. So we're going to start by diving straight into some examples. And in this next example, we're told that the fourth term of an arithmetic sequence is 20. Straight away, we can go ahead and represent that information. We know that the fourth term is really A1 plus 3 lots of the difference. We can state that that's equal to 20. And the 13th term, we know, is equal to 65. So if we know that the 13th term can really be written as the first term plus 12 lots of the difference, will then equal to 65. And what we have now is we have a system of linear equations with 2 unknowns. And so we're going to go ahead and solve that system of equations in the same way that we would solve a system of equations in Algebra 1. Let me pause for a moment and give you an opportunity to just solve that. Okay, welcome back. So as you can see, I decided to go ahead and solve my system of equations using elimination and establish that actually the value of the common difference is positive 5 and that the value of the first term is also positive 5. And so if we know that in general for an arithmetic sequence, the rule for the nth term is always the first term plus n minus 1 lots of the difference, we can come up with an explicit rule, and actually we can go ahead and simplify that explicit rule. So we get 5 plus 5n minus 5. We'll end up with an is simply equal to 5n. And so if you want to work out the first 5 terms, well, a1 is going to be 5 lots of 1, so that's 5. And at this point, since we know it's an arithmetic sequence, we are expecting it to go up by that constant difference. A2 would be 5 lots of 2, which equals 10. And really at this point, the next few terms are relatively straightforward to go ahead and establish. So to show that the sequence is arithmetic, we need to actually show that there is a common difference. In general, we know that the difference between the next term and the current term is always fixed at D. And so we just simply need to go ahead and establish that. So 17 minus 6, well, that really is the same as 28 minus 17. It's really the same as 39 minus 28, which is really the same as 50 minus 39, which equals the common difference, which in this case is 11. To find the general term, well, we can remind ourselves that an is really equal to a1 plus n minus 1 times d. And in this case, we can see that the first term is equal to 6, n minus 1 multiplied by that common difference of 11 gives us an is equal to 11n minus 5. And actually, in this situation here, there's a little bit of a translation trick that you can take a look at. If we go ahead and analyze the common difference is 11. And really, the rule an is equal to 11n would represent the 11 times table. Now, the 11 times table would obviously be 11, 22, 33, 44, etc. What we actually have is we have the numbers 6, 17, 28, and 39. And what you can see is that sort of a vertical translation has taken place. These numbers in black have been translated down by a value of negative 5. All right, so you can use your knowledge of transformations to begin to sort of think about what's going on here. If we want to determine whether or not the number 325 is a member of the sequence, well, we know that the rule for the sequence is 11n minus 5. And we're simply going to go ahead and say, well, look, 325, does that at all equal 11n minus 5? We can go ahead and solve that. 330 is equal to 11n. And we're going to get 330 divided by 11 equals n, which equals 30. Now, since n is an integer, we can confirm that, in fact, yes, 325 is a member of the sequence because n is supposed to represent the position in the sequence. If we'd arrived at something like 30.795, clearly, because that's not an integer value, it can't represent a position in the sequence. So, conclusion, yes, 325 is a member. Moving on to the next example now, and this is a little bit more typical of what you'll see in your quiz. We have the first 3 consecutive terms of an arithmetic sequence, and they've been expressed as 5. So A1 is 5. A2 is equal to K, and A3 is equal to K squared minus 8. To establish whether or not the value of K that makes this sequence arithmetic, we need to actually recall the definition of an arithmetic sequence. And an arithmetic sequence, we're just going to come down here for a little bit more space. A2 minus A1 has to equal that common difference. But likewise, A3 minus A2 has to equal that common difference. And so we can fill in the necessary values. K minus 5 should be exactly the same as the common difference. And another way of expressing that common difference is to say A3 minus A2. And so K minus 5 has to be the same as K squared minus A minus K. And what we're left there is a degree 2 polynomial. I'm going to give you just a moment to go ahead and solve that degree 2 polynomial and check whether or not your values for K satisfy the conditions. So what you should have established there is that the values for K are positive 3 and negative 1. And if we now go ahead and try and have a look at the 2 sequences that are generated, A reminder here about the first term, second term, the third term. When k is equal to 3, our sequence becomes 5, 3, and 3 squared minus 8 is really 1. When you take a look at this here, you can see that the common difference is negative 2. And so the general rule, well, an is going to be linked to the negative 2 times table, and we're going to need to add 7 if we want to translate that up to generate the sequence of numbers that we have. Of course, you can use the other mechanism that we developed in the first couple of examples, but hopefully by now you're developing that level of speed. When k is equal to negative 1, our sequence is 5, negative 1, and then of course if we've got negative 1 squared minus 8, really what we've got there is negative 7. And again, if we analyze, we can see the difference here is a common difference of subtract 6. So an is really equal to negative 6n plus. And to translate up there, we're actually going to have to translate up 11. Okay, so in addition to being able to establish this explicit rule for an arithmetic sequence, we're also going to look at finding the sum of the terms in an arithmetic sequence. Now, I'm going to give you a moment to just pause through and read through the following notes before we take a look at the next example. So if we want to find the 150th partial sum, it really means that we want to find the sum of the first 150 terms. So some of the tools that we're going to need to know, we know that the sum of the first n terms is n over 2 times a1 plus an. So if we want to find the sum of the first 150 terms, it's going to be 150 over 2. We can establish that the first term is 6. What we don't know is what the 150th term is. So to do that, we're going to need to do a quick analysis and actually work out the explicit rule and then use that explicit rule to find the 150th term. So let me give you a moment just to do that. So hopefully you spotted that this is really just the 6 times table, so the rule right here is just an is equal to 6n. We then take a moment to go ahead and work out the 150th term. We plug that 150th term in, and then it's just a case of evaluating the formula. In terms of the next example, what we have is a quick application problem. So let me give you a moment to just read that through and have an attempt yourselves. So a couple of key things to pay attention to. First of all, the first year resulted in 160,000 worth of printing paper being sold. And each year we want to increase that sales revenue by 20,000. And we want to do that for an additional 9 years, meaning we want to see what happens after 10 years of sales. So really what we're doing is we are going ahead and establishing the 10th partial sum, the sum of the first 10 terms. And to do that, we know that we're actually going to need to know the 10th term. Hopefully you went ahead and you established what the explicit rule was for this formula. You can either do that by plugging and channeling into this formula, or perhaps you notice that really this is just the 20,000 times table that's been vertically translated up by a factor of 140,000, so we need an additional 0 here. Once you've gone ahead and established what the 10th term is, you simply go ahead and plug that into your formula, and you should have established that 2.5 million was the total sales for the first 10 years of operations. On to the final example for today. We want to go ahead and find the first 2 terms of an arithmetic sequence where the 6th term is 21 and the sum of the first 17 terms is 0. Let me give you a moment to have a go. So hopefully you realize you need to express all the given information in terms of the first term and the common difference, and you've gone ahead and you've built 2 equations with 2 unknowns. Let me give you a moment to take a quick look and then go ahead and solve the system. Having solved the system, you should have established that the common difference was -7 and the first term was 56, and this allows you to confirm that the first term is 56 and the second term is